right, let's get started. So I want to continue with my TDA plus X journey. And today we're going to talk about a special one that kind of it's very kind of hot off the press. It's just come out like earlier this month, basically. Sorry, just a second. My video is doing something funny. Don't know why. Okay, let's see if this is better. Okay. All right. Okay, so I'm going to talk about today is the combination of TDA and data sketching. So how many of you have heard about the word data sketching before? You can raise your hand, or you can, kind of put a chat. How many have you heard about PCA before? Yeah. So PCA, in some way, can be considered as a way of data sketching. So today, what we're going to look at is a connection between topological data analysis and data sketching, and it's a very recent project. And it's actually led by one of your fellow classmates, Minja, who's here, and two of my other PhD students. Okay, so essentially the main idea is, can you combine the idea of data sketching, is this specific case called matrix sketching, with topological descriptors? And in this case, topological descriptors is what I call merge trees. Okay, so what do I mean by that? First of all, the motivation, of course, coming from scientific data analysis. And in this particular case, this is something called corner flow. This is called corner flow data set. What's happened is that, this area, those are basically, think about them as solid walls. And you have some sort of fluid that start from here and kind of flow and avoiding those boundaries. And what you see, the color, is what we call the magnitude, the velocity magnitude. Okay, so it somewhat captures certain patterns in the flow. Okay, and specifically in this case, I'm just looking at the critical points in here, and I'm only looking at local maximum and saddle in the scalar field. So when you actually have flow data, what you usually do is you see this kind of sort of circular patterns, and then the circular patterns sort of capture some of those flow patterns. But in this particular case, we want to have an ensemble of the simulation. So this is, for example, this is time 1, this is time 7, this is time 9. I don't remember exactly time steps, but this is a time varying flow. So as you flow from lower left corner to the upper right corner, as your time goes on, this underlying scalar field will change, as one way to look at the changes in the underlying physics, but also you can look at the change of the corresponding, in this case, merge tree of this corresponding instance. Okay, so the idea is that if you give me this time varying data set, which I could treat it as ensemble, meaning that every time step is a particular instance, so it's a collection. The idea is, can I use some sort of topological method to find representatives, which is, okay, if you think about a time varying data set, maybe the topology for a period of time, it doesn't change, and then it will change, and so on. So can we find representatives that correspond to different topological changes in the data? And outliers are the ones maybe kind of stand out as a particular instance from the data, as well as the final goal is to obtain what's called compressed representation. And I will make that clear very soon. The compressed representation, meaning that I actually want to reduce the entire collection of my data to only a few instances that sort of explains the entire set. So this is where the sort of connection to PCA comes in. All right. So how do I formulate this? The formulation is as follows. if I have, for example, a number of scalar field, so in this case, I'm showing you some synthetic data set. I have 3 different scalar field. And the middle picture, this is sort of the plot of the terrain, right? So the blue area in here are sort of, think about them at the bottom of the lake. And then if you look at here, this is sort of the visualization of the graph of this function. So I put the bottom of the lake kind of sorted in the height direction. So this is sort of like, think about it, visualizing my scalar function as a terrain. And then this picture here is the merge tree, right? Remember, if you have a merge tree, you're looking at the sub-level set of the function and how sub-level set component are born and merge as we go along. This picture here is actually, we kind of embedded the merge tree in the domain itself, right? So again, if I think about a height function, I start with some low height function. I'm looking at what's below it. So in this particular case, if I look at what's below it, I have 3 components that is born. So that corresponding to the 3 node that correspond to local minimum. As I increase my height value at this stage, the 2 branch of the merge tree were combined with each other. Let me use red instead. So you have, as we go along, there's 2 components. And if I go pass through here, I get additional, there's additional component that's born right here. And I pass through the next saddle point, this component, those 2 components in the sub-level set will merge. This will keep growing and so on. So it merge again, and then it goes to the global maxima, right? So what I drew here is sort of how the merge tree is embedded in the domain. And here, this is just the more abstract view of the merge tree where the line is straight line, but then the critical point here, the leaf of my merge tree corresponding to the local minima of my domain. Okay, so this is something you already seen. So what is the overall picture? The overall picture is that if there is a collection of scalar field that's coming from some scientific simulation, and each scalar field give rise to a merge tree, okay? So now you have a collection of merge tree. The question, which is kind of interesting, is can we find a basis set, so a smaller set of a merge tree, such that every tree in this large collection can be approximately reconstructed from the linear combination of the merge tree in the basis set. Okay, so this might be a little bit foreign to you, but if I just think about T to be collection of high dimensional vector, and I'm going to find a basis collection of high dimensional vector such that every input vector is a linear combination of vectors in my basis. This is essentially along the line of PCA, right? Because if you think about, what does PCA and all those matrix sketching does, the very naive understanding of it is to say, oh, I have high dimensional points. I have a bunch of high dimensional points. Okay, I mean, I'm drawing it in 2D, but imagine they're high dimension. And let's say I'm going to find some basis. And because I'm in 2D, I'm going to find maybe 2 basis vectors. And I happen to find, like one basis vector is going to be here because they're vectors. So I'm just going to, do it like this. And then this is my first vector. Maybe this is my second vector, right? So this is my S1 and this is my S2, lowercase. And such that every single vector, for example, this particular vector is now a linear combination of the basis vector. So this is sort of like a coefficient A1 times S1 plus A2 times S2, right? So this is sort of, think about this as, well, I want to express every single high dimensional vector as a linear combination of my 2 basis vector. Okay, so that is something hopefully you are a bit more familiar with, is to try and find basis among high dimensional vectors. Now, imagine what we're doing is we're replacing each of those points by a tree, specifically by a merge tree, okay? So now the interesting question is, now if you give me a collection of merge trees, right? This is, let's say this collection has 3 of them. Can I find a smaller basis set, which is also trees, such that every single tree in my input collection is now a linear combination of them? Okay, that is sort of what I mean by compression. Because I have a collection of more complicated structures, I want to reduce that collection to a smaller set so that every single element in my input tree is going to be a linear combination of this small basis set. Okay, so let me make it more formal in terms of PCA or matrix sketching. Okay, so we kind of know how to deal with this when I have high dimensional vector. Okay, so now let's get back to the more high dimensional vector setting. I have a set T. T is now a collection of high dimensional vector. The idea is to find a basis set such that each vector in my input is reconstructed from a linear combination of vector in my basis set. Okay, so what is in my basis set? What's in my basis set is basically what's in this B matrix. Okay, so this is sort of formulated in a very generic way, but typically in both PCA and what's it called, so there's PCA is roughly formulated in this way, and then there is also what's called column subset selection. We'll make that clear soon, but let's think about this, right? This also shows up when you do dimensionality reduction using PCA. So the idea is the following. My data, I have n data point. So this is 1, 2, up until n. So I have n data point. Each data point is of dimension d, okay? So in some sense that every single column in my data is a high dimensional data point. So matrix A encode my input data, right? It's a D by N matrix where each column is a high dimensional data point. Now, what I do is I try to find an approximation of my data matrix by something that is called A hat, okay? When I say approximated, there's some sort of nice property I'm trying to preserve. For example, one example is to say A and A hat, their Frobenius norm, which is a norm to measure the distances between 2 matrices, is roughly, close, right? So that's one way to think about it. But let's say A hat is somewhat an approximation of A. So what does that mean? That means a column of A hat, which is AI hat, is going to roughly, the hope is that they are roughly approximating, okay? So, but how do I get A hat? Usually A hat is done by finding a sort of a decomposition of my matrix into matrix B and matrix Y. And matrix B, the difference between matrix B and matrix A is matrix B has the same number of rows. However, it has number of columns that is much smaller than the original input size, right? And then what is Y? Y is what's called a coefficient matrix. What it says is that if I take the columns of B and multiply it with the entries in Y, it tells me how I'm approximating AI hat as a sort of linear combination of columns in B. Does that make sense so far? This is a classic setting of PCA, actually, right? So what happened in PCA is people actually end up treating Y matrix as the reduced, each column of the Y matrix now is a sort of reduced dimension of the original data point. The original data point is of dimension D. Now the projected dimension is of dimension K, right? K is, for example, equal to 2. That means you're projecting all the points into a 2-dimensional space. But what boiled down to is that every single entry, right? So basically this Y matrix provide the coefficient of explaining, so in a way that you can say AI hat is in some sense a linear combination. Let me use a coefficient. Let's say the coefficient coming from this column, but let me do it as, so, let's say it's y1. Well, it's a little bit misleading using y, so let me call it coefficient, maybe c1 times b1, c2 times b2, and so on and so forth. So a1 hat is now a linear combination of the columns of b. Okay, so we know how to do this. Like I said, PCA does exactly this. Okay, so how do we actually translate this formula to the what I want to achieve here, which is I now have a collection of merge trees and I want to find a basis to represent the collection of merge trees. So in a way that when I combine topological data analysis with data sketching, what I'm trying to sketch is no longer just high dimensional vectors. I try to sketch some more complicated structure, okay? And I've been asking myself this question for like 2 years until recently we figure out how to actually do it. So how do we do it, right? So the picture you just saw, there's a notion basically is to say a set of high dimensional vector is in somewhat sketchable via matrix sketching. And you can consider the principal component analysis, PCA, and column subset selection are both types of matrix sketching. And we just kind of explains in PCA when you find a decomposition of matrix B and matrix Y such that A is approximated by the matrix multiplication, where in PCA the columns of Y is used as a low dimensional projection of AI. So AI corresponds to YI. In column selection, it's slightly different, is to say that in PCA, the columns in B may be new vectors, right? Because as you see this picture, in order for me to find a basis, I'm going to choose, like the x-axis as one basis, y-axis another basis. They are not element from the original high dimensional point cloud. But for column selection, which is a different type of matrix sketching, is that in order to formulate the columns of B, the columns of B are selected among the column of capital A. So in a sense that the bases that we are choosing are a subset of the element of the original input. So that's called column selection. Literally, our basis is selected among the input high dimensional vector. Okay, any questions so far? Okay, so moving on. Because we know how to do matrix sketching, meaning that I'm going to find matrix A hat that approximate matrix A such that A hat can be factored into matrix multiplication into what I call B matrix and Y matrix. And B matrix is somehow give rise to my basis. Each column give me the basis. Y matrix give me the coefficient. So, this is exactly what PCA does. If we want to do, again, A is my data matrix. B is what I call the one that encodes my basis, where each column is form an orthogonal basis for a subspace. And then Y is called coefficient matrix, where each column encodes the coefficient for approximate AI using the basis from B. And PCA can be formulated as an optimization problem that minimizes essentially the Frobenius norm between A and its approximation, where its approximation A hat is a multiplication of B times Y. Okay, so PCA essentially, by setting K, let's say if K is equal to 2, then it's just to say that my B matrix has 2 columns. And the idea is to try to find a minimizer of B times Y to minimize the Frobenius norm differences between these two. And then once you find it, each of the column can be approximated by a linear combination of my columns in the B matrix. So this is basically a formulation of PCA in terms of reducing the Frobenius norm, which also is basically try to find the corresponding embedding, which is represented by lowercase yi along this subspace. Okay, so this is sort of like a formal formulation of what PCA does. Now, if I want to use this framework in sketching a collection of merged trees, there is a few steps if I want to use this framework, right? So this is what we can do. The pipeline to try to sketch a collection of merged trees by taking advantage of matrix sketching is by converting every single input merged tree into a high dimensional vector. So in this particular case, in step 1 and 2, what you do is to say, well, I have a bunch of merged trees that is coming from my scalar field, and I'm going to translate each one of them into a high dimensional vector. So each of the merged tree now became a column, right? It's become a column in my high dimensional input, okay? And now I'm going to run the matrix sketching framework as before, right? As if I'm just doing column selection, for example. And then once we have done that, I still need a step where for each of those sketched, for each of the approximated tree, I need to convert it from a high dimensional vector back into a tree. So that's what's called a sketched merge tree. And then for each of the spaces, I also need to take the high dimensional vector back into a tree. And that's called a basis tree. Okay. And what we report on is to say what is a collection of the sketched merge tree and what is a collection of the basis tree. So in a way that I'm saying that, okay, through this matrix transformation, now if you give me a collection of input merge tree, they become a linear combination of those basis trees. Okay. Any questions so far? All right, let's go into the detail again. Step 1 is in the actual technical detail, right? So if you think about the following, I want to take advantage of matrix sketching to approximate complex topological structures. And the first step is to say, how do I convert each of the merge tree into a high dimensional vector? There's many ways to do this, okay? But one of those ways, which we're going to explain today, is to represent every single merge tree as what's called a metric measure network. And I will define it very soon. And then once you convert it to a metric measure network, you can match each tree to a column vector. And one of the major important questions, hopefully by now, it will come to your mind, is that what if my merge tree is of different size, right? If you look at this tree and this tree, they are different sizes. The first tree I pointed out has 6 nodes. The second tree has 7 nodes, okay? So somehow when I embed them into this column, I need to kind of be able to convert them to be of the same size. So somehow I need to convert trees of different sizes into vectors of the same dimension. Okay, so that is the first tricky thing to do. The second tricky thing to do, if you imagine in the classic sketching framework, in order for things to be sketched, if I have 2 vectors, and if I have a fixed dimension, this particular dimension of those 2 vectors have somewhat of a correspondence between each other, right? So in a way that if I convert my merge tree into this high dimensional vector, I also need somewhat of correspondence among a fixed dimension between those trees. In other words, that I need some sort of structure correspondences between these merged trees to make my sketching to make sense. Okay, so for example, if I give a very simple merge tree example, let's say this is tree 1, this is tree 2, and tree 2 and tree 1 is almost the same, except that maybe tree 2 has a little extra branch. So when I think about converting both of them to a high dimensional vector, what has to happen is to say, okay, you know, if I have some sort of a structure correspondences in visualization, is also called feature tracking. But if I have a structure correspondences, I most likely will be say, well, the root of those two trees correspond to each other. The internal node, yellow, corresponding to each other. The left root corresponding to each other. And now I have a choice. Maybe I want to say that the right branch, I would say roughly that this node may be corresponding to this entire side of things, right? So I have a somewhat of a structure correspondences, and specifically, we are using some sort of probabilistic correspondences to have correspondences between those two trees, which means when they are converted to a high dimensional vector, there are some correspondences between dimensions, okay? So that's step 1 and 2. Now, step 3 is what I just explained, is what's called matrix sketching, and there's 2 types what we do. One is called column subset selection. Column subset selection is the one such that the matrix B is formulated by selecting some column from matrix A. So the basis that I'm formulating is coming from the original input, okay? The second is called non-negative matrix factorization. It's actually really factoring the matrix into a matrix B and matrix Y. So matrix B, the columns may not come from the original input. Okay, so it might be some new basis that I'm trying to find. Okay, so once we apply this matrix sketching, we know that the matrix A is now approximated by matrix A hat, where A hat is where every single column of A hat is a linear combination of columns in B. So my B is the matrix that encode my basis vectors. Each column is a basis vector. So now what we need to do is to take each approximated column of A hat. So we know that A is approximated, AI is approximated by AI hat. So for every AI hat, I want to convert it back to a tree. So that's what's called a sketched tree. For every column in matrix B, I'm going to convert it back to a tree. And that's what we call a basis tree. Okay, so that is step 4 and step 5. So my output will be, give me a collection of input merge tree. I output for each input merge tree its sketched version and the basis trees. And of course, the coefficient matrix, okay? So let me give you a very quick example. This is sort of a synthetic example. On the left-hand side, what you see is a time, it's sort of a scalar field that is a combination of a mixture of Gaussian function. And so it has some bumps and it has some mountaintop and it has some valleys. So think about the valley as a lake, mountaintop at the tip of the mountain. So what we do here is we are only focusing on the merge tree of minus f, which means it's actually the merge tree of inverted function. So my leaves of my merge tree are my local maxima. So in this case, I have local maximum here, local maximum here, and a saddle here. Another way to think about it is that I have this mountain like this, and I have a height function, and I am inverting it to be minus f, and I'm computing the merge tree of minus f. So merge tree of minus f is sort of computing, looking at the super level set of this function. So another way to think about it is that there is the 2 local maximum. I'm looking at everything above it. So there's 2 components. As I decrease in my function value, they will merge into one another. Okay. So that is sort of the merge tree construction. Of course, when I drew it, I flipped it upside down. So the bottom line is that I have this 12 instances, And the way I generate it, because I want it to be smooth and time varying, is if you look at this particular, bump right here, it's kind of just rotate in the domain as I go along, whereas the other Gaussian functions are fixed. So this one kind of move, it goes around and so on, and and it's move here and here and here. Anyway, so it's kind of move around, and we'll take the sum of this Gaussian. That is my synthetic function. And what's happened if you look at the corresponding merge tree, right? Again, this is a merge tree involving invert of this function. So, the leaves of this correspond to the local maximum. So the bumps of this function. What you see on the right-hand side is, if you look at the merge tree, there's actually some structure changes, but pretty mild, right? So in the first picture in 0, there is sort of like 2 leaves. In 1, there's additional bump. So there are 3 leaves. In 2, there's 3 leaves. In 3, there's 2 leaves, and so on. So you kind of have this entire collection of merge tree on the right-hand side. Okay. So now, if I want to select a basis, and I'm using column selection, right? CSS, which is column subset selection. What I get is actually, if I choose to say I only want 2 basis trees, the basis that's chosen is actually tree 4 and tree 7. Okay, this is where this framework becomes interesting, because if you think about it, I want to choose bases so that every other tree can be expressed as a linear combination of those bases. The idea is I actually want to choose the bases to be as orthogonal as possible from each other. So in a way that their underlying structure should be quite different from each other. So that's what I mean by when you select the bases, you will end up selecting good representatives of this entire collection. If you see I selected tree 4 and tree 7, their structure is quite different, right? That's number 1. And number 2, they are also a good representation of the entire collection. Why do I say by that? If I go back to the matrix formulation, let's say each of those input merge trees is converted to a matrix, well, a high dimensional vector. This is how the high dimensional vector looks like. Because I have exactly 12 trees. So each of those columns in my matrix A corresponding to a high dimensional vector that encode information of each of those input tree. My A hat is the approximated matrix out of matrix sketching. Okay, my B hat is because I said, oh, my K is equal to 2, meaning that I want to choose 2 basis trees. Okay, so that's why B is of 2 columns. But in this case, I am using IFS, which is actually a specific type of column selection. So you know that what's in the matrix B is 2 selected columns from matrix A. So in matrix A, I choose 2 of those columns to be the basis. And then those 2 columns happen to corresponding to the 2 tree, which is tree 4 and tree 7. Okay? And then Y is the one that is most interesting. Y is now the coefficient. How do I read this? The first row is a coefficient for the first basis. The second is a coefficient for the second basis tree. So if I focus on a particular column, let's say the first column of matrix Y, what is telling me? It's telling me, roughly speaking, that tree 0, which is the first tree, can be approximated as some coefficient of the first basis tree plus a coefficient of the second basis tree. So this coefficient, let me call it C0 and C1. What is C0? C0 is very close to 0. So that means most of the coefficient is contributed to the second basis tree. Are you still with me? So what this means that for the first basis, for the first input tree, It's a linear combination of the two bases where the most coefficient goes to the first, well, there's two basis tree. There's this, I'm using S0, S1. So 0 basis tree and first basis tree, S0, S1. Okay, so they're all 0 index. So it just means that it's very much focused on the second one. What is the second basis? Oh, sorry, what's the first basis? Let me get it. I got it other way around. Yeah, so it's actually the first basis tree. This is tree 4. No, this is tree 4. This is tree 7. Okay, this should be the right one. Okay, so my ordering changed a little bit. So if you look at the tree 0 versus tree 4, they are very close to each other, which means tree 0 is a very high coefficient times tree 4 and almost 0 coefficient with tree 7. Now, if you look at tree 1, it's very close to tree 7, which means it's going to have a high coefficient for tree 7 and low coefficient for tree 4. That's exactly what you see here. This is tree 0, which is the first column. Tree 1 is the second column. Does that make sense so far? Okay. And similarly with tree 2, right? So tree 2 is again similar to tree 7. Tree 3 is similar to tree 4. So you see this kind of like consecutive yellow band or yellow blocks that can be used essentially to cluster my input into two groups based on their similarity with respect to the underlying basis trees. Okay. Now what I show in the bottom here is a sketched tree. So I have not explained to you how do I convert it back, but let's say I have a way to convert a high dimensional vector back to a tree. So in this case, what's in the blue box is the original input tree, and what is in the red box is a sketched tree, meaning that, you know, for each of those columns, for example, here, there is a particular input tree. And now if I did matrix sketching, I'm going to take a column of A hat and convert it back to a tree. And that's what you see in the red box. So think about 3 as an input tree in blue, and then the bottom in red is a sketched tree. So because you're using matrix sketching, what you expect to see is that maybe there's small changes, but roughly speaking, your sketched tree should look very similar to your input tree. All right. So that's what you see. If I look at tree 3, before and after sketching, they look almost identical. If I look at tree 8, there is a bit of a difference. There's, for example, this branch still appear to be the same, but there's a switch between this branch and this branch. Okay, so yes, so there are some structure differences. And same thing with 9. 9 probably is not as bad as 8. Okay, but you see that 9, maybe this sketched version has a little bit shift in terms of height function value. Okay, but roughly speaking, I get a reasonable representation of my original tree and then sketch tree. And when I say you have a compressed representation, now your entire collection of input tree, where there's 12 of them, can actually be expressed as 2 input tree and a coefficient matrix. Sorry, 2 basis tree and a coefficient matrix. So essentially your matrix B right here and your coefficient matrix, then combined, now kind of represent the entire collection of my merge trees, right? So that's what I mean by compressed representation, is that I take a very large collection of merge trees, I reduce it to be represented as a smaller, much smaller, in this case, only 2 basis trees together with a coefficient. So every single tree now is a linear combination of those basis tree. Okay, so that's what I mean by compression, is that I reduce the entire large collection of trees, merge trees, into a smaller collection of basis trees. So that is a problem setting. Okay. Now, remember I said there's column selection to form matrix B. There's also matrix factorization. And then this is another matrix factorization, which is called non-negative matrix factorization, where again, I'm going to get A approximated by A hat, which is equal to B times Y. And in this case, B is obtained by factoring the matrix. So B is not selected as columns from A. Okay, so in order to do that, we're going to see the algorithm very soon, but you can also get, again, setting two bases. I'm going to find two new trees such that they serve as bases. So this is what you see. Those these things in the green box are now the basis tree I obtained through matrix factorization. So they're not coming from the original input. So they're not original input tree. But if you actually compare them with respect to the one that is coming out of column selection, which is tree 4 and tree 7, if you actually look at these two trees that is coming from factorization, they're actually quite similar. So what does this mean? This means for this data set, if I choose two brand new trees to be used as a basis, they happen to capture, again, two different merge tree structure that represent the underlying collection. And then another thing is that if you look at my matrix Y, which is a coefficient based on this new two bases, you will also see a similar structure as before compared to this matrix Y here, right? So this is a different Y. So this coefficient is coefficient with respect to two new brand basis tree, versus this coefficient is with respect to two basis tree that is choosing as part of the input tree. Okay, but you will still see a similar clustering structure of the input, meaning that, tree 0, tree 2, tree 3, they are very similar to the second basis, and versus tree 1 is very similar to the first basis. Okay, any questions so far? Okay, if there's no questions, let's take 5 minutes break, and we'll be back at 9:59 to continue the rest of it, where I'm going to spend mostly energy explaining the technical formulation underneath it. Okay. All right, let's come back to any questions so far? I know this is sort of a little bit dense, but I'm trying to give a very sort of hot off the stove kind of research of TDA and data sketching. All right, so actually Mindra pointed out to me, indeed, I was uploading the wrong coefficient matrix. That's why it was switched. Let me kind of share with you the correct one. I'm not going to update the slides for now, but I'm going to show you the, so the original matrix in my slides, I have the order of the bases switched. So this is the right order, okay? Meaning that, you know, the first basis tree is tree 4 and the second basis tree should be tree 7, not the other way around. All right. Okay, so let's get back to the slides itself. Okay. How do we actually do this? Okay. There's some quick review over merge tree. And then the most important part, that is technical part, is called Gromov-Wasserstein distance for measure network. And I will spend some time explaining that. But let's first take a quick look of the matrix sketching techniques. So I will only explain one of them, and the other ones, they are all boiled down to matrix operations. So this is what's called CSS corresponding to column subset selection, but column subset selection has two different variants of how you actually implement it. And then the one that I'm explaining now is what's called modified length squared sampling. So what is a high level picture? I have a matrix A, and I want to select a subset of the column of A to be used as my basis vectors. In order to select it, the high level picture is to select the column that has the largest norm, largest squared norm. Okay, so there's two variations, of course. In this case, I can select the one with the largest squared norm, or I can select the one randomly proportional to the squared norm. What does that mean? That means that if you have a large squared norm, there's a higher probability of it being selected. Okay. And then once you select that, you of course remove it from the future candidate. I selected this column, I don't want to select it second time, so I remove it from my matrix. And now what's interesting in this step is that I would like to factor out the component along this selected column. So essentially, if you look at the step 3, what it says is that once you have selected a column to be your basis vector, I want to select the next basis. But I actually want my next basis to be in a way that is orthogonal to the one I just chosen. So if I have another column that is very close to the column I have already selected, if I do a projection, along this direction, I am going to get a very small squared norm. So in a way that by projecting along or factor out the component along the existing direction, I kind of try to enforce it for my next basis vector to be chosen to be almost orthogonal to the one I just chose. Is this making sense so far? So the idea is I want to choose distinct columns, okay? So, and then of course you do this after k steps, and you choose k columns to be your basis. Okay, so that is a column subset selection algorithm called LSS, and this is the one that we're going to use most for our real world examples. The second one is slightly different. Again, it's called IFS. It's called iterative feature selection. It's also a column selection strategy. What it does, it starts with a random subset of columns and kind of improve it over time. Okay, I'm not going to go to detail, but again, it's idea of try to select a subset of my columns so that, it has somewhat of a distinct from each other. And then the last one is what I call non-negative matrix factorization. What it does is try to find matrix A hat that is close to matrix A in terms of forbiddenness norm. But in this case, the matrix B chosen is a new set of vectors that is not coming from matrix A. So it's not coming from existing columns from A, but some new matrices. Okay. So those are, there's even more matrix sketching, but we just experiment with those three. Okay. And it's called non-negative is because I want to make sure that my matrices that is factored out is non-negative. Okay. And then there's a reason for it, and it will be clear later why we want those to be non-negative, because I translate each input merge tree into a vector where the vector encode pairwise distances. So if you're thinking about pairwise distances, the pairwise distances is usually non-negative, okay, in a graph. Okay, so merge tree is something you have seen before, right? This is a topological descriptor that records the connectivity among the sublevel set of a scalar field. And it's related to Moore theory and so on. So again, if I take a threshold, let's call this, sorry, I think just a second, I think my pen just ran out of ink. Juice. Okay, all right, good news, I have a backup one. Okay, good. So if I choose a particular threshold, A, if you look at the merge tree as well as the original scalar field, you are looking at essentially what's at the sublevel set of this function. So you see there's one component here, and then there's another component. And correspondingly, there is one branch of the tree, and then there's another branch of the merge tree. Okay? So that's a merge tree, and you have seen this before. And this is, of course, the mathematical definition of the merge tree. You have a height function over a domain. In this case, I have a two-dimensional height function. A merge tree studies the connectivity among the sublevel set of the function, which is all the things in the domain that has a height function below or equal to the threshold. And then 2 points are considered equivalent if they are having the same height function, or if they're at the same height, and then they belong to the same connected components of the sublevel set. And the merge tree is sort of the quotient space. So in another way to think about the merge tree, it's a tree structure where every single vertex in this tree structure has a function value, right? For example, this particular vertex, which is a saddle point right here, has a corresponding height value attached to it. So another way to think about a merge tree abstractly is a tree with a function defined on the node of the tree. And the way I typically visualize it is I sort the function value from the smallest to the largest, okay? So in this case, of course, local minimum are the leaves of this tree. Okay. All right. So the most crucial technical part actually coming from a line of work, which is called Gromov-Wasserstein distance. I'm going to call it GW for easy pronunciation for the rest of the lecture. The GW framework is coming from a line of work by Mamoni back in 2007, 2011. There's a work from 2016. The one that is closely related to what we do is actually coming from a work in 2020. So it's very, very new, right? So this is from Samir and Tom. What they looked at is that if you have a pair of network, in our case, the network happen to be simpler, they are trees. If you have a pair of networks, you want to kind of find a matching among their nodes. And then the matching is in somewhat probabilistic, okay? So I want to find probabilistic matching between a pair of nodes. So this is really crucial when I mentioned before, not only I have a pair of trees, I want to map each of those trees into a vector of the same size, but also there has to be some structure correspondences for this whole framework to make sense. So I need to find correspondences between two trees that is very similar to each other, okay? So this is what's called probabilistic matching, which means that for a pair of node from tree 1 and tree 2, I want to see what is the probability they are going to match with one another. And because it's a probabilistic matching, it means some node might match to multiple nodes, okay? So actually I missed some green stars in the picture. I'm just going to add it back. There's another green star, there's another green star, okay? So what is this picture telling me here? There is what I'm saying here is that there's a particular way to compute this matching, and that's through the GW framework. And I think we'll have time to explain this framework today. So what's happened is that if you look at two trees, two merged trees, ignore the star for now. I have those two merged trees. The first tree on the left has 8 nodes, right, including the root. It has 4 leaves, 3 internal nodes, and a root node. The second tree in the middle has 6 nodes, okay? So now I want to match a tree, which is also a graph, with 8 nodes against a tree with 6 nodes, okay? So I want to figure out some sort of matching between the nodes. And what you see on the right through the GW framework, it gives you one of those matching. And then the color corresponding to yellow corresponding to high probability and blue corresponding to 0 probability. Okay, so the color map is right here, going from 0 to up to 0.12. Okay, so what happened here is that if you look at this, each of the row corresponding to a node from the first tree, each of the column corresponding to the node from the second tree. So the node is also ordered from 0, labeled from 0. So the left one has node from 0 to 7 from the first tree, and here has node from 0 to 5. So 0 to 7 across 0 to 5, right? So it's the size of the first tree cross the size of the second tree. And then entry corresponding to the matching between them. So if you look at the first row, which is node 0 from the first tree, it's matched with a high probability to node 5. What does that correspond to? That corresponding to the root of the first tree mapped to the root of the second tree. Okay, good. Now let's look at the second one. Actually, let's look at number 4. Number 4 from the first tree is now matched to 2 nodes from the second tree. So this node 4 here is matched to node 1 and a node 0 and node 1. Okay, so if you look at the probability, what it says is that this node 4 is matched to node 0 with probability 0.08 and mapped to node 1 with probability 0.04. So it's a slightly higher probability to match to node 0 than match to node 1. Okay, any questions? No?
We can see here not just node 4 maps to nodes in tree 2, right? There are many other nodes that has 2 non-zero elements in the row.
Yes, I just give 2 examples.
Mm-hmm.
Right? For example, node 5, if I want to look at node 5 is this node. Node 5, like this row, node 5 is mapped to node 4 and node 5. So what is node 4? It's matched to node 4 here and node 5 here. Okay? So in some sense, if I read every single row, I have some sort of probability coupling. And then the property of this matrix here, which is this coupling, it has an interesting property. If I sum over each row, this is 0.15. This is 0.15. If I add all the entries, okay, so each of this entry is 0.15 of 0.12, sorry. And then 0.12, there's a total of 8 rows. If I add them all together, it's 0.96, which is close to 1.0. Okay. Now, if I add all columns together, each column is 0.16. This is 0.16. And then there's a total of 6 columns. So 0.16 times 6 is also 0.96. So it's also close to 1.0. And this is by design. And I will explain that to you soon. Okay? So this is my probabilistic coupling. So I know that a node can be coupled with multiple nodes. Now, let's go back to the high-level picture. The high-level picture, okay, so I know that between a pair of nodes, I can couple them onto each other. But actually what we need is even a little bit more involved, because I want each of those trees to be mapped into a vector of the same size. So instead of coupling them onto each other, I actually want to couple each one of them or match each one of them to the same tree. So this is what I call tree T hat. So T hat is in some sense a structural average of those trees. Okay, so T hat is a tree where, think about it as an average tree between these two input trees. And the idea is tree hat is slightly larger than each one of them. And now, instead of coupling T1 and T2 against each other, pair against each other, I'm going to try to pair each one of them to this average tree and look at the probability matching between them. So because if I can match each one of them to the average tree, now I can use the label from the average tree to represent each input tree. And because they are all matched to the same average tree, I can convert each of those input tree into a vector of the same size, because I'm just going to use the label coming from the average tree. So let me make it more clear. The average tree, there's a way to compute it. The average tree in this for this two tree happen to be a tree of 12 nodes. Okay, so this has size 12. And I'm also going to use the GW framework to couple each of those input tree T1 against T hat. Okay, and then I'm going to look at the coupling matrix here. So if you look at this, tree hat has 12 nodes, but what it does is actually duplicated some nodes. Okay, so for example, right around here, there is actually 2 nodes that is actually sitting on top of each other. I just duplicated it. I just made an extra copy of it. Okay. So now if you look at the coupling between T1 and T hat, again, now the rows of this coupling matrix are the vertices from the average tree. So there's 12 rows. The columns are the tree from first tree 1. It has 8 columns. So if you look at the coupling, what do I see here? If I look at the 10th row, which is for the average tree, which node corresponding to node 10? So node 10 is what? The root of my average tree. And that is coupled with 0, which is the root of T1. Okay. Now, if I look at both, you can look at either row 0 or row 3, but let's look at row 0, right? Let's see the node 0 right here, which is, you know, with a green star. Node 0 here is coupled with node 4, right? What is node 4? Node 4 is this node right here. And same thing with node 3 is also coupled with node 4, which is also this point. Okay, so that is the coupling between the average tree and the first input tree. Now I can have the coupling between the average tree and the second tree. Again, I'm going to focus on node 10 of the root. So if you look at node 10 of the root, this corresponds to node 5, which is the root of the tree. Okay. And again, what is node 0? Node 0 here corresponding to node 0 and 1, which is these two trees, these two nodes. Okay, so in a way, what we're doing here is to say that, okay, I have a collection of merge trees. They are all of different sizes. And in order for them to be converted to the same vector of the same size, I'm going to use a label coming from the average tree. So I take the entire collection, I compute an average tree, and then I match each of those input tree to this average tree. And then based on this average tree, I can convert each of the input tree to be a vector of the same size. Okay, so how do I do that? I need to skip a few scenarios to tell you how do I do that exactly. So this is a sort of the measure network step that I was describing before. In order to find the coupling between things, I am going to define each of this merge tree as if there's a probability distribution on it. And the probability distribution, in this particular case, we're using uniform distribution, meaning that for every single, if I have the size of my tree has V number of nodes, then every node has 1 over V of probability. Okay, so basically, if you sum over all the probability over the nodes, is sum to 1. That's why I showed right here where, roughly speaking, if you take each of this row and each of this column, they all sum to a number that is close to 1. And because for the first tree, it has 8 nodes, then the probability on each of the node is roughly 1 over 8, versus the second one is 1 over 6. Okay. All right, so this is a coupling. I haven't told you how this is happening, okay? So the first thing we are doing is to go back to the GW framework, and I think I just have enough time to explain that, and then for the next lecture, I'm going to finish the rest of my talk. So when you have two matrices, okay? When you have two graphs, let me actually describe it here. Wait, where? I think I missed a slide, sorry. Oh yeah, so this is explained here. So every single tree or single graph is represented by 3 things. The V is a node set, the W is a weight matrix, and the P is a probability on the node. As I mentioned before, the probability is just 1 over the size of the graph or the tree. The weight, the weight, you can be any sort of weight. In our setting, the weight on a particular edge in the tree, so for example, the weight in this edge is a height function difference between them. So the weight of, let's say this is node X, this is node X prime, is a difference between the height value, okay? And then if I have 2 nodes that is not adjacent to each other, for example, let's say node X and node X double prime right here, then it's the shortest path based on pairwise weights, okay? This is actually key to our framework. This is the one way to encode the structure of the merge tree into the weight matrix. And then that weight matrix is what we use to convert the tree into a vector. Okay, so how do I convert a tree into a vector? I have this merge tree in here, and I look at, essentially, I convert this to a pairwise distance matrix. So let's say this one has n number of nodes. So I have my weight matrix, W, is of dimension n by n, where each entry is a pairwise distances between them. And remember I said, if they're adjacent to each other, it's just their height function difference. They are far away from each other, then it's the shortest path based on these weights. So this become a matrix, a pairwise distance matrix. And then I can linearize it. So how do I linearize a weight matrix? I convert it to the first row the second row, the third row, and so on and so forth. I can take this pairwise distance matrix and convert it to a vector. That is how I convert a merge tree to a vector. Okay. However, well, how do I even get to this step, right? This first step, like I said, I need to be able to turn them into the same size. So this is what I need to do, is I need to kind of define a mean or average, and everybody will match to that average, okay? So this is maybe the most mathematical component, and maybe we can resume next lecture from here as well. But let's say I have two graphs. In this case, we're using graph, and tree is a special type of graph. I have V1, W1, P1, and G2 is V2, W2, P2. Okay, so it's vertices, weight, and probability. The distortion of a coupling between these two is a sum of over essentially all pair of edges that is in some sense matched into one another. So there's kind of loss function, and you can change that loss function. But what you see here, the first term, W1 IK, is for a pair of edge in the first graph that is matched to a pair of edge in the second graph. And then the C is a coupling matrix you see right here that is visualized. So think about C as a probabilistic matching between those edges. Okay.
So I have a quick question.
Yeah.
So when you say a pair of edges, does that mean that the vector, I guess, would have every like permutation of pairs of edges?
So when I say this, if you look at what is Cij, right? Cij is to say a node from the first graph is matched to an ith node from the first graph is matched to a jth node of the second graph.
Okay.
Remember? So C is a coupling matrix, right? If you look at this coupling matrix says node 5 from the first graph is mapped to node 2 of the second graph. Okay.
So every time you're saying pair, you mean just that closest matching from one to the other?
Yes. Yeah. So, okay. So you are looking at, well, I mean, there's maybe, in this particular example, a lot of entries is 0, but there may be, for example, in this case, I can have, 0.8, 0.08 matching and 0.04 matching, right? So I can choose one.
Mm-hmm. Yeah. Mm-hmm.
Okay. So what you have here is that, okay, let me get back to here, is that for a pair of, so I have a node I from the first graph, it's mapped to node J from the second graph. And node K is matched with the first graph, mapped to node L from the second graph, okay? This is the matching between the nodes. This is one of the probabilistic matching. And then this is a probability notion, right? I'm looking up into that coupling matrix. Now, the weight is between node I from the first graph and node K from the second graph, right? Which define an edge, or, a weight. There's a weight of those two pair of nodes, right? And then there is a weight between J and L, which is double arrow from the second. J is from a second graph, L is from a second graph, that corresponding to a pair of nodes from the second graph. And then this first term is sort of a loss term, which is essentially, think about it as measures the similarity between these two pairs. Does that make sense so far? In other words, if I and J are very close to each other or very similar to each other, and K and L are very similar to each other, right? Then the loss is going to be very small. So you basically, this is optimization process. This is if I have a fixed coupling, this is what I call distortion, right? So I want the weight between the edge that connecting IK from the first graph and an edge connecting JL from the second graph. I want them to be as close as possible, right? And then this is distortion is defined over a fixed coupling. And what we actually want to do is to minimize this coupling. So I want to minimize this distortion. I look at all possible couplings between the nodes, And then this is our optimization process itself. And specifically the loss function L, you can use it as a square loss. So it's just the weight difference squared with some coefficient in the beginning. So if you look at this formula, what do I want to do? I want to look at among all possible matchings between the nodes, I want to find the one that minimizes the distortion. Okay. And that's the GW framework. At the end of the day, when I optimize this equation, I will find the best coupling matrix that minimize the distortion. Okay, so again, let me give a very precise example. If I say node 0 is mapped to node 5, and somehow node 1, by some coupling, not this one shown here, let's say node 1 is mapped to node 3. Okay? If I impose along this particular coupling or matching between the nodes, then it's possible that the weight between the green edge and then the weight between these two nodes, their weight difference is going to be large. So this is not an optimal coupling, because if I actually couple them this way, I'm going to introduce a large distortion. Does that make sense so far? So when I optimize a coupling, I actually want to more or less kind of have a coupling that respect the underlying structure. For example, in this case, 1 is mapped to 2, probabilistic speaking, and mapped to 3. So in a way that this probabilistic matching have a better respect with sort of the underlying structure. And it has a high probability of matching to 4, then it's matched to 2. Okay. I'm going to stop the thing and we can resume next lecture from here.